The ideal gas law, PV equals nRT, also gives us a chance to calculate other properties of an ideal gas that may be useful, particularly its density and its molar mass. These are relatively direct derivations from the ideal gas law. Remember, density is always a mass over a volume. Of course, we have volume V in the ideal gas law, but we don't have mass. We do, however, have moles, N, of the gas, and we can rearrange the ideal gas law to have moles per volume equal to the pressure over the gas constant times temperature. Since we often convert moles to mass using molecular weight, it should be no surprise that we can do the same thing here and multiply both sides of the equation by molecular weight. Since the number of moles times molecular weight gives us a mass unit, the right side of the equation becomes mass over volume, a density unit. We use the Greek letter rho to indicate density. That's the one on the right that looks like a fancy P. If we happen to measure mass, volume, pressure, and temperature, we could find the molecular weight of a substance, or if we knew the pressure, temperature, and molecular weight, we could find the density of a gas. We can think of the derivation specifically for molar mass as well. Molar mass is mass over number of moles. It's difficult to measure the number of moles. Even if molecules are standing still, I lose track after about 5, which is a long way off from 10 to the 23rd. It's easier to measure pressure, volume, and temperature, which the ideal gas law tells us is equivalent to the number of moles. If we substitute PV over RT for N in our original molecular weight equation, our equation for molar mass becomes mass times RT over PV. So if we measure temperature, mass, pressure, and volume, we can easily find molecular weight. We now add our final ideal gas law, Dalton's law of partial pressures. Dalton noticed that if non-reacting gases were added together under the same conditions, the pressure of each of the added gases added to make the new total pressure. This follows pretty directly from the ideal gas law. If volume and temperature are held constant, pressure varies directly with the number of moles and can be used as a proxy. But Dalton came up with this in like 1802, so it preceded the ideal gas law and was pretty novel at the time. If we know the total is just the sum of its component pressures, we can also use the percent composition of the total to give partial pressures, the pressure of any individual component. For example, dry air, that's air without any humidity, is 21% oxygen or so. If there is 1.000 atmospheres of air in the atmosphere, the partial pressure of oxygen is just that 1.000 atmospheres times 0.21, the decimal for 21%, which is equal to 0.210 atmospheres. If we think about this in another unit, in kilopascals, which is actually helpful for our next problems, if there are 101.325 kilopascals of air, try to figure out what the partial pressure of oxygen would be. We take 101.325 kilopascals, the equivalent of 1 atmosphere of pressure, and multiply by 0.21 to get 21 kilopascals. So there's 21 kilopascals of oxygen in a normal atmosphere of air. We can use these percentages the other way too, though. For example, the minimum safe pressure of oxygen is 16 kilopascals. If we know that percent oxygen stays the same, we can say that the atmospheric pressure times that percent equals 16 kilopascals. Solving for the atmospheric pressure gives 16 kilopascals over 0.21, which is equal to 76 kilopascals. For a person of average health to breathe sustainably, they must have at least 76 kilopascals of oxygen pressure. This corresponds to the oxygen pressure that's around 2,400 meters or 8,000 feet. And most people will actually pass out once they get to around 4,600 meters or 15,000 feet. This matters a lot to climbers because Mount Everest is over 8,000 meters tall, with atmospheric pressure of only about 33 kilopascals. The astute among you notice that this is less than 76 kilopascals, and the particularly astute notice that this is less than half of 76 kilopascals. See if you can figure out what the actual pressure or partial pressure of oxygen is here. To find this out, we take the atmospheric pressure at the peak of 33 kilopascals and multiply by the 0.21 composition of oxygen to find that there are only 6.9 kilopascals of oxygen available. Many climbers attempting Everest will use supplemental oxygen, but there are purists who decide to attempt Mount Everest without any oxygen, requiring them to be in particularly good shape with particularly high hemoglobin levels to get all the oxygen they can. Partial pressures aren't just important to climbers, they're also particularly important to divers. A diver needs to limit the amount of oxygen to which they are exposed. For a 45-minute dive, the limit is 160 kilopascals. But there needs to be enough density in the tank that it doesn't float, otherwise you might as well be snorkeling. And the overall pressure needs to help with the increasing pressure of the water depth, so you can keep breathing against that water pressure. This means diving tanks must be pressurized at 6 bar. 160 kilopascals is less than 6 bar, so we need to make up the difference with other gases. The question is, how much? There are 2 steps to this: converting bars to kilopascals, and then taking the difference. See if you can solve the problem on your own, possibly referring back to your last set of notes for the bar to pascals conversion. A bar is exactly 10 to the 5th pascals, or 100 kilopascals. So we multiply 6 bar by that conversion factor to get 600 kilopascals. The difference between the 600 kilopascals and the 160 kilopascals of oxygen is 440 kilopascals of other gases. Dalton's law gives us a good way to think about inert gases, gases that resist reaction. Many gases are actually formed from or participate in reactions, which requires collection to analyze. One way to do this is to take an Erlenmeyer flask and fill it up with water. The Erlenmeyer flask can be inverted into a pan of water, preventing the water from flowing out without creating a vacuum on the top of the glass. Any reaction-producing gas can have the gas routed into the Erlenmeyer flask, and as long as the gas isn't water-soluble, it will back up into the Erlenmeyer flask until the pressure on the inside equals atmospheric pressure. What we're really interested in isn't the volume of the gas, which we can measure with the volumetric markings, but the number of moles. We can convert volume to number of moles as long as we know temperature, thermometer, check, gas constant, check, and pressure. Pressure is a little bit more difficult, but here's the trick. The level of the water inside the flask will be equal to the level of the water outside when the pressure is equal. You can control the pressure to atmospheric pressure by moving the flask up or down so that the pressure adjusts. That gives us a pressure reading that may be pretty close, except that water can evaporate and contribute to the overall pressure. Water does this predictably. The pressure measured must be adjusted to account for the pressure from the water vapor. If the experimental conditions were standard ambient temperature and pressure, the total pressure would be 760 torr, but 23.8 torr of that would be from water vapor pressure, leaving only 736.2 torr from the gas itself, which would be the pressure that we'd actually want to put into the ideal gas equation. Gases can be products as well as reactants. If the entire reaction takes place in the same conditions, same temperature and pressure, the volume of a gas reacting will be proportional to the number of moles and give us the same ratio. For example, if we have 1 mole of nitrogen, it will take up just shy of 25 liters of space at standard ambient temperature and pressure, which is 1 atmosphere at 298.15 Kelvin. We represent that 25 liters as a balloon. Similarly, each mole of hydrogen will take up about 25 liters of space, for a total of 75 liters for hydrogen. When these react to form a product, though, only 2 moles of ammonia are formed, which means that they will only occupy 50 liters of space. When we have volume of gas, we can use it along with temperature and pressure conditions to get to moles of a substance using the ideal gas law, and we can use those to get quantities of another substance after a reaction, just like we saw in the last chapter. If we get it into moles, we can find quantities for pretty much anything else in the reaction. When we mix gases, there are 2 important properties to note about gases related to that mixing: effusion and diffusion. These properties give us an intro into one of the most important theories of phase, the kinetic molecular theory, which we'll deal with in the next section. Suppose we have 2 containers connected by a closed stopcock, as shown in diagram A. We have hydrogen on one side and oxygen on the other side. Within these vessels, molecules are moving and colliding constantly. Whenever they collide, it's like a pool table. The molecules bounce off each other and head in new directions. Also similar to a pool table, the harder you hit the cue ball, the more the other balls bounce around. At the molecular scale, this corresponds to higher temperatures. If you shrank the pool table down, they would also have more collisions since there's less area to not collide. That corresponds to an increasing pressure or decreasing volume on a molecular scale. So molecules will collide less if they move to where there are less things for them to collide with. It doesn't matter what type of particle it is. So if we open the stopcock as shown in B, some of each particle may move to the other container. Any container that has fewer particles will have fewer collisions, meaning the molecules will change direction less often. Any container with more particles will have more collisions, making it more likely that the particles will, over time, move to a less concentrated area, which we call diffusion. This always happens over time, and eventually everything spreads out, as shown in C. This can happen at different speeds depending on the size of a particle. We compare this with the rate of diffusion, just the amount of a gas moving through the area over time. Rates of diffusion are faster when concentrations are very different and when the flow is unrestricted. Rates of diffusion are also faster when they involve molecules contributing to the sense of baked goods. I call this Graham's law. While diffusion is the best way to describe movement of a gas that's mostly unrestricted, this changes if we're talking about a very small hole that allows gases to move through. Gases are generally spaced out significantly at standard temperature and pressure, so the volume of a gas is mostly empty space. It's tempting to think that with a small hole, the smallest things will move through faster because they fit through the hole better. But every molecule is going to fit through the hole just fine. Molecules are very small. They're instead differentiated based on how fast they move rather than their size. This process is called effusion, the movement of particles through any hole that's smaller than the root mean path, a measure of the amount of space a molecule takes up before it hits another molecule. In these systems, only one molecule on average can move through the hole at a time, because otherwise it bounces against other atoms and moves them out of the way. We aren't limited by the molecular size, but instead by how quickly the molecules get to the hole. The fastest molecules are the smallest at any given temperature. This makes sense because temperature is a measure of the average kinetic energy of a system, and kinetic energy is a factor of mass, but also velocity squared, and they're inversely related. If the mass doubles, the velocity squared needs to be halved to have the same kinetic energy. So large molecules end up being much slower. So when the movement of molecules is controlled by a very small hole, in effusion, the rate of effusion is inversely proportional to the square root of molecular weight. Again, large molecules must be much slower at the same temperature, and they effuse much more slowly. If you want to compare two molecules, the ratio of the square roots of molecular weights gives the inverse of the ratio of rates of effusion. If the molecular weights are known, the relative rates of effusion can also be known by the equation shown on the bottom. This is employed industrially in the process of enriching uranium, changing the ratio of uranium-238 that can't be used for fission to uranium-235 that can. When uranium is harvested, either by mining or seawater extraction, all available isotopes are harvested according to their abundance, not really selectively at all. Uranium-238 is by far the most abundant, but uranium-235, the one that most people want to use for fission, also exists. All isotopes are converted to uranium hexafluoride. Uranium hexafluoride sublimes at around 57 degrees Celsius, so a slight heating can produce gases with slightly different molecular weights. The faster moving uranium-235 hexafluoride can effuse more readily across a porous barrier. It can effuse faster, leaving behind uranium-238. The differences in those effusion rates are actually really small, since the molecular weight differences are a very small percentage of the mass. The uranium hexafluoride that passes through an effusion barrier needs to be further enriched to continue to remove uranium-235 over many iterations. They call these sequences cascades, which may have thousands of units. While this technology continues to be used to enrich uranium, it's gradually replaced by centrifuges that take advantage of small differences in those gas densities. They also require cascades of centrifuges, but require much less energy to operate.